Hello everyone, welcome to Saurav's classes. So we have a function sine of log x greater than 0, and we want to see if it's increasing, if it's bounded, if it converges or doesn't. So there's a set of properties given in the form of options. Let us try to check how this function behaves as x goes to infinity. So firstly, we all know that the sine function oscillates and doesn't converge as x goes to infinity. We can always find a 2n plus 1 pi by 2 where the sine function is 1 or minus 1. Now sine of log x is oscillating as log x goes to infinity. We have x goes to infinity, which implies log x goes to infinity, which implies sine of log x oscillates. This is true because once again we can just have x for which log of x is equal to some 2k plus 1 pi by 2 for more and more bigger case. Hence sine of log x oscillates. However, sine of log of x is less than equal to 1, so it is bounded. Now we have a function which is bounded as x goes to infinity and it does not converge, so C is the correct option. Now let us look at the next problem. For any two functions f1 and f2 from closed 0, 1 to r, we have to define g as the max of f1 and f2. So the options are, if f1 and f2 are linear, then g is linear. If f1 and f2 are differentiable, then g is differentiable. If f1 and f2 are convex, then g is convex, or none of the above. So let us take an example, a graph. This is 0 and this is 1. We have a function like this and a function like this. We can take this function to be say fx equal to x, and we can take this function to be fx equal to minus x plus 1. So at 1 it takes the value 0. Yeah. So for these two functions, let's see how many counter examples we can get. Now what is g now? Since g is max of f1 and f2, g is like this. So of course g is not a line, hence g is not linear. At this point we have a steep edge, and so g is not differentiable. Now we can easily, safely cross out a and b. What about c? So let us draw another graph of a function 0, 1. Let this be f1 and let this be f2. For these two functions f1 and f2, we know that f2 is concave and f1 is convex. In such cases, we can have problems because the max g is convex in some places and concave in some places. However, if we have f1 and f2 both convex, if G is differentiable at a place, if G prime X exists, it implies that G prime X is equal to F1 prime X or F2 prime X. Similarly, G double prime X exists implies G double prime X is equal to F1 double prime X or F2 double prime X. So now we know that both these are greater than 0 if our functions are convex. Therefore, G double prime X is also greater than 0. Hence, the maximum of f1 and f2 as a function is also convex if f1 and f2 are both convex. Hence, C is the correct answer.